Welcome to mini lecture number 2 for module 5 on samples and sampling distributions. In this mini lecture, we're going to look at sampling distributions of the mean and the central limit theorem. And in this, we'll talk a little bit about the fact that we take samples from populations, but how well do samples represent the true population mean? We're going to cover standard error and the role of sample size on influencing the size of the standard error, and the central limit theorem. And we're going to do this by working through some examples. So here is data for a population of all men on blood pressure. So assume that the population distribution is given by this information, and we have mu, the population level mean blood pressure at 125, and the standard deviation for the population mean at 14 millimeters of mercury. So suppose that we had a lot of time and we decided to do an experiment. And so we're going to take 500 separate random samples from this population of men, and each time we're going to sample 20 individuals, right? So 20 individuals, we're going to take samples of 20 individuals 500 times. For each of those 500 samples, we're going to plot a histogram of the sample blood pressure values and record the mean and standard deviation. So here are two samples that were done with 20 individuals each. Remember, there's 500 of these. You can see here plotted the distribution for the 20 individuals in each of these samples, and at the bottom there's the mean represented by X bar and the estimated standard deviation for each sample. And notice that there is some variability in both the mean, so it's 125.7 for sample 1, 122.6 for sample 2, and again there's 500 of these that were done. Now this figure is showing the histogram of the 500 sample means. So of the samples that were taken, some of them had sample means that were just over 115. Some of the sample means were as high as 135, but there's a normal distribution here of sample means, and the mean of the sample means is 125 millimeters of mercury. The mean of the means is referred to as the estimate, and then we have the standard deviation of the sample means, and that is called the standard error. So the standard deviation of the distribution of means, which is what we're looking at now, this is the 500 means from the samples that were taken, is called the standard error. And the standard error is the uncertainty in our estimate. Okay, so this is based on taking sample sizes of 20 individuals. So say we have lots of time on our hands and we decide to do another experiment. This time we're going to sample 50 individuals at a time and record their blood pressure, and we're going to do that 500 times. Okay, so for each of those separate 500 samples, again we're going to plot a histogram of the blood pressure values and look at the sample mean and sample standard deviation. Okay, so here again is sample 1 and sample 2 of 500. Each of these now has a sample size of 50 individuals. The means and the standard deviations are listed below, and again there's still going to be some variability in the means of these different samples. So this time we're plotting the histogram based on just the means of those 500 samples. Again, it still looks quite normal. The mean is 125 millimeters of mercury, and the standard error, right, that's the standard deviation of the means, the standard error is 1.9 in this case. And this is smaller than when the sample size was 20. When it was 20, the standard error was 3.3. And we're going to do this again. So now we're going to do these 500 separate random samples of men, and now each time a sample is going to have 100 individuals in it. and we're going to plot the same information a third time. And at this point, you should be able to think about what's going to happen to the overall estimate of the population mean and the standard error. Okay. First, we're just going to look at a couple samples. So these are 2 of the samples with 100 individuals. Again, we're still getting some variation in our means, but it's smaller now that we have 100 samples than it was when we had 20. And when we look at the overall plot of the sample means, so these are the 500 means of the samples, and each sample had 100 individuals in it. And our mean is 125, which is the same as it was previously. And the standard error is now 1.4. So as we have larger and larger numbers of individuals within a sample, our standard error for the estimate of the overall population mean gets narrower and narrower. So let's review what we looked at here. So the population distribution of the original individual blood pressure measurements for men was normally distributed, and the true mean population blood pressure was 125 millimeters of mercury, and with a standard deviation of 14. And then when we took our 500 random samples, you can see that on the table the sample sizes are listed on the left side. The means were all the same, but you can see that the standard deviation of the sample means, or the standard error, gets smaller and smaller as our sample sizes increase. And all of those distributions look normal. So that was when the original data looked normal. Now let's see what happens if we examine some data. This is data on the length of stay of patients discharged in 2005. And the distribution shows that most individuals were released after quite short stays, and some individuals were released after longer stays, but we have a skewed distribution here. The population mean is 5 days, and our standard deviation is 6.9 days. So now we're dealing with highly skewed data of our original population. So similar type of experiment. We have lots of time on our hands. So we're going to take 500 separate random samples of the population of patients. Each one is going to have 20 individuals in it. And we're going to plot the same information that we plotted previously. So these are data for 2 of the samples. Now we have 20 individuals in each of our samples, and our mean and standard deviation from these samples is listed below. And they look quite variable at this stage. Interestingly, so we did this 500 times, and we take all of them, just the means of those samples, and we plot them, and what we get is something that looks fairly normally distributed, even though the original data is not. And the key here is that although the original population data was highly skewed, when we look at just the means from all of our samples, that has a normal distribution. And the mean and standard error are shown there. Now we're going to do this with a lot more individuals. Now we're just going to jump right up to 100 individuals within each of our samples, and we're going to do that 500 times. So here's our plots with 100 individuals. You can see that they still look quite skewed. And when we plot the means from each of those samples, again, it's normally distributed when we're looking at the means, and our standard error is quite small now. So it's gone down to 0.78 days. And so when we look at the results of this, the means of our 500 sample means are all right around 5, so they're quite close to the true mean of 5, and then our standard error gets smaller as our sample sizes increase. And that despite that we had right skewed data originally, the shape of the distribution of the means are still approximately normally distributed. And we can see that the just emphasize that our standard error gets smaller as our sample sizes get larger. And the fact that we get an approximately normal distribution of the sample means, even if the original data is highly skewed, is due to what is called the central limit theorem. And it says that for any population of scores, regardless of form, which means the distribution of the original data, the sampling distribution of the mean approaches a normal distribution as n, our sample size, gets larger. And that the sampling distribution of the mean has a mean itself, the expected value, equal to the population level mean, mu, and a standard deviation or standard error that's equal to the standard deviation of the population divided by the square root of n. And so, again, if n gets larger, right, then the denominator is going to be larger, which will make this whole thing smaller. So that would lead to a smaller standard error. So to put this in context, on the left-hand side here, you can see the blood pressure data, and on the right-hand side is the length of stay data. And I've shown the actual population data at the top, and then for the different sample sizes at the bottom. And you can actually see how the standard error gets smaller as the sample sizes increase. And that regardless of the population level distribution, the distribution of the means is normally distributed. And because the distribution of means is normal, and this often happens around a sample size of 30 is typically what you see in the literature, because this distribution of means is normal, this allows us to further investigate means because many statistical tests assume that means have a normal distribution. And this ends mini lecture number 2 for module 5.